It sounds too crazy to be true, but can a tiny elementary particle really be God? Surely, you've heard of the God particle that scientists in Switzerland have been able to locate. These scientists have now announced a puzzling discovery at the Large Hadron Collider in Geneva. The particle suddenly exhibited unexpected behavior that calls everything into question and shows in a shocking way that we can never know everything. The mystery of the Higgs boson, a brand new discovery, shows that our previous understanding of the particle may have been wrong. This could shed a whole new light on a discovery that changed the world. Before we continue with what exactly scientists were able to observe at the particle accelerator in Geneva, we'll introduce you to the Higgs boson in a little more detail. To understand what particles and God are all about, we need to take a little trip into quantum physics. This is the science of the smallest particles. Quanta are particles of light, or photons, tinier than atoms, and they were long considered the actual building blocks of matter. But then researchers figured out that there are even smaller particles, and even smaller particles, and so on. Particle physicists are looking for these particles and want to use the discoveries to decipher how matter is built in the nucleus and how it's created. The Higgs boson appears in the matrix of the smallest particle where mass is concerned. The Higgs boson gives mass to other particles by interacting with the Higgs field, an invisible energy field that permeates all of space. We can see particles with mass above a certain density, so this is where what we can perceive as visible creation comes from. Light, for example, we cannot see while it travels through space. Light also has no rest mass, we see it only when it is reflected by particles with mass. You can see this in the very simple example that it is bright on the surface of the Earth when it is illuminated by the sun. The universe, on the other hand, is dark, although masses of light particles travel through and come to us, for example, from distant stars. So, we could say that the Higgs boson and the Higgs field appear exactly at the place where visible matter appears. And God said, "Let there be light." With this, we can already answer the question asked at the beginning. No, the Higgs boson is not God himself, but it appears at a divine magic threshold, which has an interesting connection to religious ideas. The discovery of the Higgs boson was a milestone in particle physics in 2012, and scientists were able to use the discovery to defend the Large Hadron Collider, as the particle accelerator had previously come under heavy criticism. Some opponents of the facility are even of the opinion that the experiments there could create black holes or bring the entire universe to collapse. More on that in a moment. Now, let's first look at why scientists were so shocked when they experienced something completely unexpected with the Higgs boson. The particle suddenly disintegrated under the eyes of the researchers and proved to be highly unstable. This does not fit at all with previous theories about the nature of the Higgs boson and could undo all the achievements of tracking down Higgs bosons. We take a more vivid look at what Higgs bosons are. Imagine the universe as an ocean filled with an invisible substance called the Higgs field. In this ocean, a shark swims elegantly and gracefully. It interacts optimally with the surrounding medium, almost weightlessly and efficiently. This is similar to the way certain particles, such as photons, interact with the Higgs field and are therefore massless. Next, think of a human being swimming in water. We humans have learned to swim, and we can stay in this medium for a certain amount of time and also achieve a certain efficiency. At some point, however, we would run out of air while swimming, and our mass in the strange element would be our undoing. These swimmers are similar to electrons and quarks interacting with the Higgs field, they have mass. Now imagine a plastic bottle floating on the water. It is there, moved and carried by the medium, but it has no momentum by which it actively interacts with the medium. This corresponds to heavier particles like the W and Z bosons. They interact a lot with the Higgs field, which is why they have a lot of mass. Now imagine the waves created by a shark, a swimmer, and a plastic bottle. These waves are like the Higgs boson. When a particle interacts with the Higgs field, it can create a disturbance or a wave. When we discovered the Higgs boson at the Large Hadron Collider, it was like seeing these waves in the ocean. The waves proved that there must be entities or objects or particles moving within the medium and interacting with the Higgs field. The problem that has now been revealed is that the Higgs boson does not exist for long. Once created in particle collisions, the particle remains stable for less than a trillionth of a billionth of a second, or more precisely, 1.6 times 10 carat minus 22 seconds. This is a magnitude that our minds cannot imagine. Only mathematical formulas or computers can come up with and express such magnitudes. But how can this be? How can it be that of all things, the particle that gives mass to others through interaction is itself so unstable? It would be possible, of course, that the Higgs boson gives up its own mass and thereby itself decays rapidly. But then new questions arise, like where did the Higgs boson get its mass from, and how does the transfer or creation of mass happen? Of all things, the area of creation where matter is created turns out to be highly unstable. This seems to be a paradox, and thus it would not be the only one in natural science. The fact that these small particles exist only so briefly and act in time periods that are not detectable for us makes it difficult to study them. Does this mean now that we will never get to the secrets of the origin of matter? Scientists do not give up. One way physicists study the properties of such short-lived particles is through their decay modes. Decay happens in a variety of ways, and which one occurs depends on the specific conditions. The Higgs boson decays into a different group of particles, which we'll look at again in more detail using the ocean as an example. Imagine that the waves in and on the ocean become too large. At some point, they collapse and form many smaller waves or currents. Imagine then that these smaller waves represent other particles. Depending on the original size and energy of the large wave or Higgs boson, it decays into W bosons, Z bosons, or tau leptons. Other smaller waves consist of leptons and photons. Further, the decay processes involve hypothetical particles that have not been observed with certainty, which makes their direct description impossible. Researchers tried several times to study this rare decay process at the Large Hadron Collider. According to the predictions of the Standard Model of Particle Physics, only a tiny fraction, about 0.15%, of Higgs bosons should decay into a Z boson and a photon. However, experimental data from proton-proton collisions performed at the ATLAS and CMS detectors between 2015 and 2018 painted a different picture. Surprisingly, the data show that this decay occurs only 6.6% of the time, a significant departure from the expected value. ATLAS and CMS, the two main experiments at the Large Hadron Collider, used strategic approaches to maximize sensitivity in detecting the decay of the Higgs boson into a Z boson and a photon. To that end, scientists now also rely on self-learning artificial and machine intelligences in experiments such as these, which are able to match measurement procedures in fractions of a second to elicit the highest possible result rate from each experiment. So far, however, even these processes have failed to produce the desired results. The realms of tiny particles elude scientists, and they are responding by upgrading technology in ever more daring ways, possibly creating problems we're not yet aware of. What exactly is happening in the LHC? Scientists chase two particle beams against each other with enormous force in the particle accelerator in Geneva. This happens in a ring-shaped facility about 150 meters deep underground. When the particle streams collide, particles are broken down into their individual parts. They react with each other, are deflected, or display previously unknown phenomena. This is how scientists try to explore the basic building blocks of matter. All they have found so far, in short, are more and more smaller particles, complex reactions, more and more possibilities, and questions instead of clear answers. The experiments provide never-ending insights into worlds that have no end. Imagine you are on a treasure hunt. You think you are close to the goal, and suddenly the way to the supposed treasure chamber takes dozens of branches, and these also have dozens of branches again, and so on. Which path to follow to find the answers that scientists want so badly? You see, this is exactly the problem of particle researchers, and this is the reason why many consider the experiments to be useless. Perhaps we humans need to accept that we can't find out everything about the nature of this world, nor can we break it down into its smallest components in order to understand it. In Geneva, researchers are far from realizing this. They meticulously continue their research and keep upgrading the particle accelerator. 3 years ago, the facility was suddenly taken offline. Critics were certain that something had taken place that was meant to be concealed. When the facility came back online in 2022, operators announced that particles were now being chased at each other with even more powerful magnets and energy beams. This may resemble madness with potentially dire consequences. Are humans playing God? Critics argue that the scientists in Geneva are handling forces with which they can never know what they will do. Disturbances in the structure of the particles could sneak out of the facility in as yet unknown ways and cause problems in the immediate vicinity, on the entire planet, or in the universe. This is a bit like when people discovered radioactivity. Pills, soaps, and even hair care products were made with radiating uranium. Nobody knew anything about the radioactivity, and only when people died slowly did the connections become clear. It was similar with X-rays as well, which were hailed as an extension of medicine. Then it became clear that these rays are also harmful, and today X-rays are only taken if there is no other way. The facility in Geneva could give us something similar. Researchers should know that particles can easily overcome the boundaries of matter, meter-thick walls or safety steel. Is science at an end? The Higgs boson has long been considered the cornerstone of the standard model of particle physics. However, these new findings suggest that the model was just a new beginning. Moreover, it has extensions or modifications whose scope cannot be estimated today. In astrophysics, the James Webb Telescope just proved that astronomers had a completely wrong picture of the beginning of the universe, and possibly there was no such beginning at all. Research and science devour billions every year. The experiments at the LHC cost millions or even billions, which are borne by the operating company CERN, sponsors, and governments of this earth. Many people are of the opinion that the money should be better invested in other things, such as climate protection or renewable energies. CERN is unimpressed, continuously emphasizing the safety of the experiments, and currently, the third run of the LHC is underway.